right, so today we're going to start on conditionals, which is module 3. So if you, especially because we're losing a day for Labor Day and we lost a day for Wednesday, I'd recommend that you start watching those videos in preparation for your lab on Tuesday. But we will probably cover enough here to get you through the lab next Tuesday. Remember, there's no Monday class because of Labor Day. We've been talking recently, since the beginning, about sequential control flow, where a program is executed top to bottom, left to right, just like we would read in English. But more complex problems require you to make decisions, or require the code to make decisions. Should I do this, or should I not do this? Should I do this, or should I do this instead? Right? And conditionals are how you can specify that code executes one piece of code or a different piece of code or one piece of code or not nothing at all. And you can specify that some under condition, that condition would be either something that's true or false, not something that's in between or something. We achieve this in C using if statements. Let me check. Yep, we're good. All right. So, and that necessitates Boolean logic, because we need to be able to make this decision. We need to have something that evaluates to either true or false. Right? Here are some basic examples of the if-else-if conditions. Now, this is not real code here, because what I've put here in this Langle-Wrangle, that's just the condition. We'll talk about that in a second. But the syntax here is we use the keyword if. Inside, then we surround a parentheses, and inside that we put our condition. We then open up a code block with the opening curly bracket and the closing curly bracket. If the condition, whatever this is, evaluates to true, right, then anything inside this code block will get executed. If the condition is false, then normal sequential flow will continue right after this block right here. So if this ends up being false, none of this gets executed. And an else statement is always going to be optional. An if statement is just an if-else-if statement without an else block. And you can specify the same condition here, but two blocks, statement A and statement B. If this condition is true, then everything inside this statement A gets executed, and nothing inside B gets executed. This is what we call mutually exclusive. Either A happens, or B happens, or B happens and A doesn't happen. One, and exactly one of those, will get executed. And the B statement here gets executed only if this ends up being false. Right? Then you can tack on as many else-if conditions as you want. In fact, an else-if is nothing more than an if condition. If I just highlight that part, you see that it's just a regular old if statement. You can tack on as many of those as you want. Condition A, condition B, condition C, executing each one of those conditions. And there are some more details here. For example, that mutual exclusivity means that order matters. The first one of these conditions that gets evaluated to true is the one that executes, and all others are completely skipped. So for example, if this is false, but then this ends up being true, then it checks condition B, and if that ends up being true, then this executes. And then the rest of it is completely skipped over. I like to jump immediately into examples to illustrate this kind of stuff. So let's go ahead and take the game last night. To all the groans in the earlier section as well. All right, so the Husker score versus the Minnesota score. We'll read those in and we'll determine who won. Now the condition to specify that the Huskers won, right? I forget what the score is. We all want to forget what the score was, but what was it? We'll eventually input that, right? If the Husker score is greater than the Minnesota score, right, then that means that the Huskers won, and we would print out printf. Yay, the Huskers won. Right, there we go. Well, there's another condition here. This condition is a numerical condition, right? I'm asking, is the value stored in this variable strictly greater than the value stored in this variable? If so, then it executes, okay? Well, let's just go ahead and compile that right now and see what we get. So GCC demo, right? I'm reading these in as command line arguments here. So I'll go ahead and input the Husker score and the Minnesota score respectively. What were they? 10, 13, right? So did the Huskers win? No. Consequently, nothing gets printed out. This is a simple if statement, right? And it evaluated to false. Therefore, this did not get printed out. Normal control flow returned here, and the program ended without doing anything. Right? Let's go ahead and add an else if condition here. Else. Actually, just go ahead and go else, right? You might think that there are only two conditions, but we'll add a third here in a moment. Oh no, we lost again. There we go. All right, there we go. It won't happen forever, but there we go. Now let's go ahead and execute that same program, and we see that the else condition executes. Why? Because again, this is false, and therefore this does not get executed. Instead, the else condition gets executed. What if I had reversed those scores? What if we got the field goal instead? Right? Then it would say that the Huskers won, but that's not what happened. Something else could have happened. If we had not thrown an interception and allowed them to get a last-minute field goal, what else could have happened? A tie. Right? So let me put in another condition here. Else if the Minnesota score is greater than the Huskers score, that's the condition. That's the real condition that we lost. There's another condition here that we could have tied and then gone to overtime. So let's go ahead and print that out. Print out. We go to overtime because football does not allow ties. It actually does. Not collegiate football, but professional football. You can go and get a tie, right? It's very, very rare, but it does happen, right? There we go. I suppose you could get a tie in collegiate if the weather doesn't permit and you just don't want to make up the game or something, but I don't know. All right, so let's see that in action. What if we had actually tied 10-10? What would have happened? This would have been false because the Husker score is not strictly greater than the Minnesota score. 10 is not strictly greater than 10. 10 is not strictly greater than 10. So we fall through here to the last one. No matter what I input, the actual, like a wishful score here, the actual score that there was, right, or the tying score that we had before, exactly one of those things gets executed, and only one of those things gets executed. Right? So there is our if-else-if example that we start out with. Okay. Again, some observations here about the syntax and such. Let's go with observations. Right? So note the style. Right? We begin the opening curly bracket on the same line as the keywords if, else, etc. Right? The closing curly bracket is aligned with the keyword. Right? That's the style that I'm going with. There are other styles out there, some uglier styles, some alternative styles are just as good. Just be consistent about it, right? So what I mean by that is I've got the F here. Right? This closing curly bracket is aligned in the same column. This one is aligned in the same column, aligned in the same column. The opening curly brackets everywhere are on the same line as the else if, or the else, right? The if, else if, or else. I've also indented everything to the same level within each one of these blocks. So indentation is important as well for good style. All blocks are indented at the same level. Right? So what if we didn't follow that convention? What if instead white space doesn't matter here? So what if we did this and we did that and we were just really inconsistent about it, et cetera, et cetera? So there's a nice little tool here. I think I might have shown it to you before, but if not, then fine. Well, I'll show it to you again. If you ever get into a situation where the style is bad, you can try to fix it with a style. Right? A style demo.c. Right? What that will do is we'll reformat your code up here. I'm going to have to close it and reopen it, and magically it's all fixed now. Right? There are plenty of online beautifiers, right? Online C beautifier, right? It makes your code beautiful, right? Here's the best one. I don't know if this is best or not, but you could have taken that, horribly mangled code here with bad indentation everywhere, right, et cetera, and I could go ahead and cut and paste this and put it over here, reformat it. Hey, great. That's what it should look like. Don't get into the habit of relying on tools like this. Write good code from the beginning. When you write an English paper, you don't write it and then go back and put in all the periods later, right? You write it while you at least have a good formatting the first time that you write it. Right? So get into that nice habit The IDE will tend to do it for you. Right? Let me cut and paste, bring it over, and fix. There we go. This particular beautifier wanted me to use 2 spaces instead of 4 spaces. That's fine, as long as you are consistent about it. That's what we're going to be grading on. Okay. And by the way, another thing here. Would those have been appropriate variable names as a review? No. What is A and what is B? I forget. Do I enter the Minnesota score first, or did I enter the Husker score first? These are way better names. Now, there is an abbreviation here of min, right? So maybe you have an argument, well, it should actually be Minnesota. There we go, like that. All right, fine. Either way. Right? Okay. Let's see. Some other observations. Right? In an if, else, if block, all blocks are mutually exclusive. Right? Again, one and exactly one block will get executed. And that's it. And the block that gets executed is the one whose condition evaluates to true first. Let me emphasize that, first. Right? In other words, i.e., order matters. Right? Generally, you place the most specific conditions first, then the most general later, right? In fact, the most general condition that you can have is no condition. The last one, which would be a catch-all, the else block. Right? If all else fails, then do this block. That's as general as it gets. You need to put that last. So order is important. If you transpose ordering, then it could give you different behavior, and your logic is flawed. Okay? Now, numerical comparisons. I use one that we understood immediately because it's what we use in math, right? You have the basic less than and greater than, right? Comparisons. Strict comparisons, right? You read this as strictly less than and strictly greater than. That's why when there was a tie, 10 and 10, it didn't get evaluated to true because it was strictly less than. You have equality versions, right? So in math, I would type something like this. Less than or equal to, or greater than or equal to. Something like that. But do you see those on your QWERTY keyboard? I don't, right? So to get that, what we're going to have to do is an approximation. If I just read those out, less than or equal to, that's what I end up with. If I read out the other one, it's greater than or equal to, right? That's the order in which you write it. Greater than or equal to, less than or equal to. Not equal to or less than, or equal to or greater than. Right? Those have no meaning or the wrong meaning in a programming language. The right one is an arrow that's used in some programming languages to indicate a mapping of some sort. Right? So those are not correct. Those are not actually supported, or you're going to get some syntax error or weird behavior out of it. Okay. Well, what if you have equality, like strict equality? For strict equality, that is, if I were in math, I would do something like this, equality. And inequality would be NEQ not equals. What you do is you draw an equal sign and then you slash through it, right? But in code, we can't do either one of those. Why? In code, what do I have with an equal sign? That already has a meaning. Right? It doesn't mean equality. What does it mean? It's an assignment. Take the thing on the right-hand side, whatever it is, and put it into the variable on the left-hand side. So that we solve that by adding 2 of them instead. And if you're in programming languages like PHP or JavaScript or a couple of others that I can think of, you would have to have an even stricter equality test by adding a 3rd one. We don't do that in C though, right? So 2 equal signs is for equality. How do I do not equals to? Well, again, you don't have that on your keyboard, so we have to approximate it. The approximation for not equals is by placing an exclamation point in front of the equality sign, not equals. So this is equals, not equals. Right? Here's an example. In fact, let's go over here to my code over here. I've already given you this so in the notes, so we can get rid of it. Right? Let's go back to 4 spaces, or a tab, I guess, is what I'm doing. 1, 2, 3, 4. Right? Let's go ahead and create a value here. Int x is equal to 42. Right? Say that we read that in from the user or something like that, and we don't necessarily know that it's at 42. How can we tell that it's even or odd? In other words, I want to print out x is even, or I want to print out printf x is odd. Right? So how do we know if something is even or odd? Divide by what? 2. So if I divide x by 2, right, then there's going to be some, in this case, 42 divided by 2. That goes into it 21 times. And now think back to grade school arithmetic when you're doing long division or whatever. We put an R out front. What does that R stand for? Remainder. So what's the remainder after dividing x by 2? 0. That tells you that it's even. Unfortunately, that doesn't work for this division. I mean, it's just going to be 21. How do we get the remainder out of this thing? We use the percent sign here. You would read this as percent sign is the division remainder operator, right? You read it as mod or modulo, right? So 2 mod or x mod 2. It's going to have a remainder either of 0, indicating that it's that it's even, or if it were 43 and we divided by 2, what would the remainder end up being? 1. If we go up to 44, the remainder is now again 0. 1, 0, 1, 0. That's how we tell if something is even or odd. So if that's equal to 0, then we know that it is even. Else, there's only one other possibility here, is that it's odd. Right? There we go. So using the modulo operator here, the division remainder operator, along with a strict equality here. I could have switched these around. What if I had done that instead? What if I had said that the odd part goes up here and the even part goes down here? What do I need to do now for my equality testing? Equals 1 is one option. What's another option? Not equals to 0, because there are only 2 options in this case. Right? So there's our example, and I'll make sure that you've got this in the notes. Right? So one way of testing it for equality. Let's see. There we go. All right. So other observations about this numerical comparison is that all operators operate on 2 operands. Operands, in other words, the left-hand side and the right-hand side, may be values, right, numericals. We call those literals or literals. It's literally 42. It's literally 101, right? Numericals, numbers, or literals, and or expressions, or variables, or combinations thereof, of them. So what I mean by that is that, let me go ahead and just create 3 variables here, A, B, and C. So this is already in the notes, A, B, and C. I can make all sorts of things. For example, I can compare A to 0. If A is equal to 0, there we go, then printf, you cannot divide by A. Why? Because it would be division by 0. So now we have a way of detecting potentially dangerous code. If you're about to divide by A, like in a quadratic formula, 2A, you can't do it. So we would detect that and say, I can't do that, you're going to have to find an alternative. Right? Or you could do, alternative, you could do the following. Let me go ahead and create, just cut and paste this, but I can go ahead and reverse it, 0A. In other words, you can, but do not do the following. Why would you not want to do that? Read the first one. Read line 19 in your head. If A is equal to 0, then print this out. That sounds good. Read the second one, line 23 in your head. If 0 is equal to A, then print this out. Does that sound right? No. So if you've ever got a variable and a number that you're comparing, make sure that the variable comes first, because that's how you would read it in your head. And if you've written it like this, it's the same thing as far as a computer is concerned, but it's far less readable. Right? You can compare two variables. Right? You can say if A is equal to B. Right? Printf A and B are the same. Great. Otherwise, else printf they are not the same. Right? So left-hand side here is a variable. Right-hand side here is a variable. You can also do full expressions. For example, that expression that would have given us an imaginary number, a complex number. If b times b minus 4ac is less than 0, then we can say print we do not support complex roots. End line. The thing on the left-hand side here is an entire expression that will be evaluated, computed, and then compared to 0 after it's done. So everything on the left-hand side of an operator like this gets evaluated first. You're left with one number, and then it's compared to that other number on the left-hand or the right-hand side. Excuse me. Right? All right. You can do something like this. If 10 is equal to 20, right? Printf, there we go. Why you can do that, but should you? No. Why? It'll never be true, right? So this is what we call dead code. That code will never ever execute, no matter what. A good compiler would compile it away, and it wouldn't exist in the final program. An even better programmer would never write something like that. Right? You can, but don't do the following. Right? Another example would be if you did if A is not equal to A. Right? Right. So it's not just values on both sides, but if you put something like this, is that ever true? No, A is always going to be equal to itself. So don't do that. Don't do this. Okay? All right. So let me go ahead and put all of this in the notes for you so you have these examples. Any questions so far? Yeah, go ahead.
Why do you use the brackets? I thought you were just supposed to open and close your curly brackets.
These brackets?
Yeah. Oh, no, that's what I was going to say.
Yeah, the opening and closing curly brackets, always put them. So you might be coming from some programming language, or in fact, it's supported in C. Let me go ahead and get rid of all this and look at this particular example. All right, there we go. Without the brackets, it's the same. In this instance only, because there's only one line of code. The second that you have additional lines of code, printf, also this. Right? Now it's no longer the same. Without the brackets, it only binds, or it's only relevant to the first line right here. So for that reason, I did just show it to you here, but I never show this at all because it's really bad practice to do something like this. Always have brackets, even if they're not necessary. Right? It groups everything in that block together. In fact, let's go ahead and find out what would happen here. What should execute and what should not execute here? So what should it print? Is A equal to 0 at this point? It's 5, so no. So neither one of those things should print, but the second one does. Why? Because without the brackets, only the next line is bound to this condition right here. What I really meant to do, as my indentation indicates, is to write something like this. Both of those should execute, or neither one of those should execute. And when I do that, now it's correct. Neither one of those will execute. Right? So always have brackets, even if you don't need them. We'll talk about that with styling later on. Right? Another pitfall that you might face would be you cannot use numerical comparison operators for strings. This would end up comparing memory addresses. It's going to look like you can do it, and the compiler is going to say, yeah, you can go ahead and do that, but you can't. Let me go ahead and put in an example here. I want to know, we don't have string variables just yet, but we can do it with an example like this. Banana, there we go. So, apple, before, banana, there we go. is this true or false? And what does it mean? Does apple come before banana? Well, I'm thinking of this like a regular old human, right? Where I'm used to the dictionary and everything. So does apple come before banana or not? CS50 dev. Sorry, I didn't do that. It crashed. Shouldn't be too long before it comes back up. Well, when that executes, uh-oh. No. All right, so it stopped entirely. CS50 dev. There we go. Let's try one more time. Yeah. Okay, so I don't want to go into private mode. Let's. Do I have anything else open? No, we're good. Okay. Quit it entirely. Clear the cache. And CS50 dev. There we go. Oh, did I type? I didn't type it right. CS50 dev. Right. And if that doesn't come up, then I've got an alternative. REPL.it. And if that doesn't come up, then I've got yet another alternative. All right. Are you going to come up? All right, restart. While we're waiting on that, not Emacs. I'm gonna have to go to a different server. All right, now I can use Emacs. Demo.c. All right, include stdio.h, include stdlib.h. And are you back? Excellent. Okay, there we go. Sorry about that. cdc, there we go. gcc, demo.c. Let me cut and paste this so that I've got it over here just as a backup. All right, get rid of that C. All right, there we go. So what is this going to print out? Well, in this particular case, apple comes before banana, just as we would expect. But let me show you that it's not actually working. If I switch these around, apple and banana, our intuition would say that this should not print out anything because banana does not come before apple, right? But it does. Right? So what's going on here? It's not actually comparing apples to bananas. It's comparing the memory address of this string and the memory address of this string. In other words, when I create a string with the contents apple, it's being stored somewhere in memory. When I create a string with the contents of banana, it's being stored somewhere else in memory. And memory has numbers, an address, just like houses have numbers, right? 1, 2, 3, 4 A Street, 4, 5, 6, 7 Z Street. Which one comes before the other one, right? Well, they're just numbers, right? That one happens to be at that point in the street, and that one's down the street, so that one comes before. But the Andersons live in the other one, and Zoe lives in the first one, right? It has no bearing on the contents of the house or who lives in the house. In this case, it has no bearing on what is in the actual string versus the other string. Right? It'll work, it'll compile, but it won't give you the results that you're looking for. So be careful. Right? And you behave. Right, there we go. All right. That exclamation point was actually a general negation operator as well. General negation operator. Right? Any statement can be negated. All you have to do is put a exclamation point in front of it. Here's an example. If I say, it is not the case that A is less than B. Right? First of all, is that natural? It is not the case that this thing. Right? That sounds awkward even reading it. What's another way of writing it? But equivalently. Right? So A is less than B. 5 is less than 10. Right? Is 10 less than 5? No. Is 5 less than 10? Strictly less than 10? No. So what would the negation of this be? How could I rewrite this so that I don't have that negation? A is greater than B? Is that correct? Greater than or equal to. Good. Right? So in general, yeah, you can write negations everywhere, but you should KISS. Keep it simple, stupid. Right? If you can write more compact, more readable, and understandable code, then that's what you do. Right? keep it stupid simple, let's say. That's better. I like that, right? Because you're not calling yourself stupid, right? Simpler code is, in general, better code. Right? Why? Because it's easier to read. Quicker to read means that it's easier to understand what you're trying to do. We also have Boolean variables, right? So C does not actually have built-in Boolean variables, right? Like true or false, right? Or anything like that. Instead, we use numbers, right? And the numbers that we use are 0 is false, anything else is true, right? In other words, 1 is true, but also -1. And -2 is true, right? 42 is true. 3.5 is true. There we go. Negative 3.14 is true. All those things are true. Why? Because they're not 0. Right? So don't just think 1 is true. Instead, anything that is not 0 is true, because that's what the negation is, right? If 0 is false, then anything else is going to be true. Right? Consequently, you could do things like this. Right? So int is student, right, is equal to 1, right? They are a student, right? Or is student is equal to 0. They are not a student. Now again, you can use any other value here. I could say 42. Right? Why? Don't get fancy. Right? Just keep it simple. Right? Keep it stupid simple. 1 and 0. Then you can use that in an expression. If is student, then printf, you get a discount on your football tickets or whatever. Right? Right? Do not write the following. If is student is equal to true, then you get your discount. Why is that wrong? Well, I said that you could say, be fancy about it and make it into 42. Now, you're a student, but do you get your discount? No, because you're checking for equality on something else that is true. Right? So do not write something like that, because 1, it doesn't work, and 2, it's terrible style, right? Does not work, and it is terrible style. Right. All right, fine. Well, if you want to get fancy, but you want to get fancy in the correct way, then you can also use the std bool library. Right? And I've already included that up here. std bool. Bool, what do you think bool stands for? Boolean, right? And if you've got a Boolean like that, you can have a variable called bool, right? Not an integer, not a double, not a float, not a char. It's just bool, right? Is student is freshman, because I've already got is student up there. And I can then use keywords true or false. Is freshman equals false, right? It is not all uppercase true. It is not capital T true. It is lowercase t, all lowercase true. Right? And then again, if is freshman, then you can have something like printf a bigger discount. Yay. Or no discount for freshmen. I don't know. Right, there we go. So what do you think, or what do you think this bool is? Is it introducing an actual new variable type? Nope. Let me show you what it looks like. Right. Define true to be 1. Define false to be 0. Right. All it's doing is fancy macros like we did with the miles per kilometer or whatever it was. Right. The preprocessor will go through your program. Anytime it sees TRUE, it will end up replacing it with 1. Anytime it sees FALSE, it'll replace it with 0. And that's what the standard library, that standard Boolean library is doing for you. Right? Use it, don't use it, either way. Be consistent about it. Right? Let's see, there we go. Oops, there we go. All right. All right. So you can also combine these into complex logical expressions. You can combine Booleans and statements into more complex what are called connectives. Right? The logical and logical or. You might have seen these before if you've ever taken a logic class or anything like that. Don't worry about it. We'll go ahead and introduce it from the beginning. In C, the logical and operator is true if and only if both of its operators, operands, are true. False otherwise. Here's the syntax. So if I just use one ampersand in plain old English, we use that as a placeholder for and, right? Simpson and Sons, right? In programming, however, we need to use two, because a single ampersand here, this is called the ampersand, a single ampersand has a different meaning. It is a bitwise and operation. So we need both of these here. Right? And here's an example. If I have two variables, example, right, is student and they are a freshman, right? Freshman, there we go, is true if and only if is student is true and is freshman is true, right? It is false when is student is false, or is freshman is false, or both are false. Right? So it's a logical and. It's both of those have to be true. Okay. The logical or is true if at least one of its operands is true. Here the syntax is different, right? There is nothing in English that implicitly means or, so we use these things. Does anybody know what those are called? What does Zybooks call them? If anybody's done their reading already. Did it give them a name? So they go by lots of names. In math, we call them Sheffer strokes. In computer science, we call them pipes. Not because they resemble like vertical pipes, but because you can use them on the Unix command line to pipe the output of one program as the input to another program and chain them in this long chain of programs. We call it piping. You pipe one into the other. You're hooking up two pipes together so that the flow goes through them. But otherwise, vertical pipes or vertical lines, whatever you want to call them. That's the syntax. There we go. Sorry. Example. If I have is student, I'm going to change that to or they're a freshman. Is true if is student is true, or if is freshman is true, or if both are true. Right? It only takes one. Right? These are not exactly negations of each other. They're not exactly opposites of each other, but they are very, very similar. Right? In fact, there's something called de Morgan's Law that I won't go over, but it is in the reading, I believe. Right? Okay. It is only false when both is student and is false and is freshman is false. There we go. Although, can you be a freshman without being a student? No, it's a contrived example. All right? Okay. All right, with the remainder of our time here, let's go ahead and try to do a really quick exercise. All right? So a decibel level, going back to football here, right? They all have these get loud and cheer on, right? And they've got the decibel level, which is never an accurate actual decibel level. But that is a measure of the loudness of something. It's actually a measure of the compression wave in the atmosphere. Right? That's how sound travels. And a decibel level of 0 to 60 is considered quiet. Right? 61 to 70 is conversational. 71 to 110 is loud. 111 to 194 is dangerous. Is there such thing as a negative decibel level? No. Is there such thing as a decibel level of a greater than 195? Yeah, right? But what would we categorize that as? Right? Extra loud, extra dangerous. That can be fatal, right? The compression wave in the atmosphere of a bomb would be fatal. Right? But I didn't really give you that specification, right, on purpose. What happens when it's not specified? Well, at that point, as a software engineer or a software developer or whatever, you have to go back to the stakeholders and ask them, what do we do if there's a negative value here? That's bad data. What should we do in that case? What do we do if it's 195 decibels and greater? Right? What should we do in that case? Right? You go back, and that's what's called requirements solicitation, or requirements gathering. You simply go back to the people in charge that are paying for the project, and you say, well, which is it? Or in this case, the instructor that assigned this as an exercise. Right? All right, so let's go ahead and do this. I'm not going to go ahead and read it in from the command line. Instead, I'm just going to go ahead and make it into an integer, decibel. Actually, that's my first question. Should it be an integer, or should it be a double? Double? Okay. We looked it up this morning, and it's rarely, I mean, of course, it can be a double, but it's rarely reported in anything other than whole numbers. Like if you look at an actual decibel level, or I don't know, is anybody an audiophile and they've got the decibel output, and is it reported in like 42.5? Has anybody seen that? No, hardly ever, right? So I'll just go ahead and keep it simple for now. Yeah, later on, you probably want to maybe generalize this, or even better yet, what do? You go back to the stakeholders and you say, do you want to support fractional decibel levels? And if they say no, okay, great. That's fine. We'll go ahead and go with integers here. Okay. All right, I want to know if it's quiet or not. If, let me write it out like this first. I'm just going to go ahead and translate this directly. 0 is less than or equal to decibel, which is less than or equal to 60. Right? And if that's the case, I will printf. This is not correct. Don't write this down. I will output quiet. Right. Yay. There we go. And the line. It's nice and quiet. Okay. All right. Let's go ahead and compile this and see if it's quiet. Remember, it's 42, so it lies between that range, right? It should be quiet. Ah, nice. Well, I should also test this in the event that it's 1,000. That's most likely fatal. Right? It's on a logarithmic scale, so that's really, really bad. Right? Right. So is it quiet? No, but it says it is. Right? Now, why is that? Let's think about how C is parsing this out. 0 is less than or equal to decibel. Is that true or false? Just the one that I've highlighted. True. Remind me again in C, what is true? 1. 1 is less than or equal to 60. Is that true? Yep. That's what's happening there. Right? Don't write things like that. But wait a second, the compiler said it was perfectly fine, but it didn't run correctly. Let me show you a new trick here. I'm going to turn on all warnings. Right? In fact, this is what the grader does. The grader has two, always for everything, we put in 2 tests to make sure that it compiles, and that it compiles without warnings. The first one, it compiles and says, great, it's valid C code. The second one goes through and does what's called linting. Right? So what is lint in real life, not in computer science? Right? You wash your clothes, right? They come out, but it's not dirt, right? It's not dirty, but you've got these little pieces of lint on it. It's not dirt, so I mean it's not bad, but it's not great. Right? We want to get rid of that dirt or that lint. Right? So what do? You take what is this? A lint roller, right? A lint roller that is kind of like a tape and sticky, and then it gets all the lint off of your clothes. Right? Nobody's that fastidious, right? I'm not. I don't have a lint roller. Right? But that's what we're going to do. We're going to ask the compiler to act as a linter. Don't find the dirty stuff. Right? The dirty stuff would be like forgetting a semicolon here. When I do that, of course it's going to come up with, there's an error there. There's no semicolon. Right? So I want you to come up with, not all the dirt, but all of the lint. WALL stands for warnings. Tell me about all of them. And when I do that, now it finds that lint. In fact, it tells me that comparisons like what I'm trying to do on this line right here do not have their mathematical meaning. In other words, it's valid C code, but it's probably wrong. Right? Thank you, compiler. I just had to tell the compiler to turn on all warnings. Right? All right, so let's rewrite this. I can't write it like this. I need to find a range. Is it greater than 0, greater than or equal to 0? And is it, decibel, less than or equal to 60? Well, I don't have the keyword and. What would I use instead? What was it? Ampersand, ampersand. Now, is that 1,000? First of all, the lint is now gone. But is that 1,000 decibel level now quiet? Nope. All right, let's go ahead and continue like that. Else if, all right, what's the next level? 61 through 70 is conversational. So I could write it, copy, paste, and get myself into trouble here. Right? 60 up to 70, and that's going to be printf conversational, end the line. Right? Is that correct? No. What happens when it's exactly 60? That's probably going to be okay, but it's really bad code. Why? I've got 2 instances here where it's 60. Okay? All right. So what should I do up here? 61, I like that a little bit better already. Right? And it's less than 70, then it's conversational. Let's go ahead and retest everything. 42 should be quiet. 65, right in the middle there, should be conversational. We're good. All right. 1,000 should be terrible. And we're good there. All right. Should I continue following this pattern, though? Remember, it's mutually excluded. It's mutually exclusive, right? What I mean by that is that exactly one of these is going to be executed, right? And only one of these is going to be executed. So if it doesn't lie between 0 and 60, what do I know already at this point in the program? It's greater than 60. Do I need this right here? Nope. I already know. If I got to this point in the program to even check this, I know that it's greater than 60. So all I need to do is check that it's less than 70. That saves on a lot of coding here. Else if, what's the next one? Loud, 110. Oops. 110. And that's loud. Right. Dot, dot, dot. Else, printf, undefined. That's what I'll do here for this. Right? Otherwise, it's loud, dangerous. I could do it really quick. Dangerous. And what was it? 195? 195. There we go. So now what's that 1,000? Undefined. Right? You're going to have to define that for me. What if I did -10, though? Did I account for that one? I wonder what's going to happen. Conversational? Why? Walk through this. Is -10 between 0 and 60? Nope, so not quiet. Is -10 less than 70? Yep. So what again? Order matters. What is the most specific condition that I would have here? If decibel is less than 0, then I will printf illegal input or something like that, whatever you want to print out, and then chain this together into an else if. And that will save it. Right? By the way, then, that relieves me of the need of checking for that. Right? And now I've got much more compact code here. The logic and the fall through, or the mutual exclusivity, the order matters. Everything else is taken care of for me. Okay. All right, I'll see you on Wednesday because of Labor Day on Monday.